Okay.
All right, let's get started. It's my pleasure to introduce Evan Schneider, who is visiting us from the University of Arizona. Evan is a finishing PhD student, and she's an expert in simulating hydrodynamic systems. And she has developed her own code to do so using graphics processing units. And she's going to tell us today what we can learn about galactic winds using this code.
Yeah, thank you very much. So thank you for having me. I'm coming from the University of Arizona, where I'm finishing my PhD, and today I'm going to be talking about work that I've done with my advisor, Brant Robertson, who's at the University of California, Santa Cruz. So this talk is going to be sort of in two parts. As Niels mentioned, I have written a hydrodynamics code that runs on GPUs, and I'll spend a little bit of time introducing that and why we wanted to do it and how it works. And then in particular, I've been using it to simulate galactic winds, so I'll also be talking about that particular application of the code. So hopefully that means there's something for everyone here. Okay, so first of all, why did I want to study galactic winds? So observationally speaking, they are a ubiquitous phenomenon of rapidly star-forming galaxies. So in nearby galaxies, this is just an image of NGC 3079, which is a nearby starbursting galaxy. We often see starburst winds that are being driven by supernovae explosions, often near the center of galaxies. Here you can see some nice H-alpha filaments that are sort of tracing this outflow. So nearby we have these nice spatially resolved observations. We also have more recently gotten observations of winds in star-forming systems at higher redshift. So this is actually a spectrum, a stacked spectrum of galaxies at a redshift of about 1.4, where you can see blue-shifted absorption in this magnesium-2 line, and that's also indicative of outflowing gas from the system. So they appear to be features of these rapidly star-forming galaxies at many redshifts. In addition, galactic winds appear to be a multi-phase phenomenon. So here I'm showing actually three different images of M82, which is the most nearby starburst galaxy for which we have many excellent observations. And these two images on the left show X-ray data, an earlier observation and a more recent one. And you can see that there's this hot plasma. Here red is 10 to the 6 Kelvin gas, and the blue or purple is more like 10 to the 7 or hotter. That is indicative, again, of starburst-driven a hot fluid that's emanating from the center of this galaxy. And in M82, we also have optical images. So here the purple is tracing the H-alpha line emission. So that's comparably cooler gas, maybe around 10 to the 4 Kelvin. And these are coexisting in this same system. Here's actually more images of M82. So this galaxy has also been observed to have molecular outflows. So here's just a map of CO intensity and velocity that shows that there's outflowing molecular gas near the disk of this galaxy. And so this really is a multi-phase wind. And in fact, we have observed that those different phases also appear to be traveling at different velocities. And so it's a very, very complex system. From the simulation side, I also think galactic winds are interesting because they are an absolute necessity for cosmological simulations if you want to reproduce features like the stellar mass function. So here is just the stellar mass function as it's observed at redshift 0, and this plot has lines from several different state-of-the-art cosmological simulations. I'm not here to argue about which line fits best. It's just a good example in the sense that in order to fit this stellar mass function, all of the simulations have to include some sort of feedback from star formation in the form of galactic winds. So you have to push gas out of galaxies, otherwise it cools and forms too many stars to match the observations. So the questions that I would like to investigate in this particular talk include how mass and momentum are going to be coupled in these complicated multi-phase wind structures. And so to sort of go over some of the things that I've mentioned so far, we think that there's a hot diffuse high velocity wind that originates as a result of the starburst from supernovae. And we have some observational evidence of that in the form of X-ray, spatially resolved X-ray data. But we also see this cooler outflowing material. And it seems to be, coexistent with the hot phase. And it's at large distances, often, more than a kiloparsec from the galaxy. And so that's, relatively far from where the supernovae are actually depositing their mass and energy. So there's a question of how that material got there. And so, there's a variety of questions that we'd like to answer about this sort of system, including where did the multi-phase material originate? Is it actually pushed out of the disk, or did it somehow form in situ? And what sets the velocity of these different phases? Yes, go ahead.
So how many galaxies is the hard, spatially resolved hard X-ray map possible?
Really only a couple. I can think of two, and I'm not going to be able to tell you the number of the other one since I'm not actually an observer. But it's very difficult because usually you don't have enough spatial resolution to disentangle the outflowing plasma from the actual X-ray sources within the galaxy, and so that's what you need the spatial resolution for.
Right.
Yeah.
But then I guess there's also all galaxies have compact X-ray sources.
Mm-hmm.
Some will produce an excess.
Right.
Bremsstrahlung emissions.
Yeah.
So there must be more galaxies then for which you have the hard X-ray supplementing the line diagnostics of the galaxy. You can't really resolve things.
Yeah, but I mean, I think there's really only a couple. It's a convincing argument because it's theoretically motivated for there to be this hot outflow, and so then because you can show that it's very likely there in the case of at least a couple of galaxies. It's I think that's a pretty decent approximation. Yeah, but certainly not one for which we have very many observations. Okay, and so there's a couple of other interesting questions. Might be how long does this cool gas survive? We see also cool gas out in the circumgalactic medium of galaxies at distances of 100 kiloparsecs, and so could that cool material have actually been pushed out of the galaxy, or did it originate in the CGM? And in particular, I was also interested in how mass and momentum is transferred between these different phases. Okay, so why haven't we solved these problems? We have, very fancy codes in astronomy, and we've been putting a lot of work into these sorts of questions. So what's the issue? And the problem, of course, is that the scales involved are huge. So if you want to look at the problem of galactic winds in particular, then you need to resolve scales of order 1 to 10 parsecs within the actual galaxy, which is the cooling radius for the supernovae. Then you have this region where the wind is generated is of order a kiloparsec or so in something like M82. Your galactic disk is then another order of magnitude in size, and if you want to investigate what's happening in the halo as well, then you need to resolve the entire halo of the galaxy. And so this is a problem that is currently beyond the scope of our codes. We can't get 1 parsec resolution out to the virial radius of one of these galaxies. And so as a result, right now people are mostly approaching this problem using idealized simulations. So either idealized simulations within the disk to study the driving of these winds, or idealized simulations of the wind interactions as it's leaving the disk. And so that's something that I'm gonna talk about a little bit. And so I don't have time to go into the background literature on this very much because there's a ton of it, and this is really an extensively studied problem, not so much from the galactic wind side, but in the context of these cloud-wind interactions. And so this is a field that goes back decades, and sort of the seminal study in the literature is one by Klein, McKee, and Cholla from 1994, and the idea was that they have a cloud, which is just a spherical overdense region, and then that cloud is going to interact with a shock this could equally well just be, a wind that's already in the box. Once the shock passes over relatively quickly, you're just immersed in this wind. And the study in this case was looking into how does that cloud then break up. What are the timescales for the instabilities that are going to mix the overdense material into the more rarefied gas? And in particular, this study was useful in that it developed a sort of characteristic time scale for the evolution of these clouds. It's called the cloud crushing time, and that just is it relates the size of the cloud to the velocity of the background wind and the cloud density ratio to the wind density in the background. And so if you scale things according to this parameter, then the evolution, at least in the adiabatic hydrodynamic case, appears to be self-similar. And so you can describe cloud breakup this way. So then there was many years and many studies, including lots of different physics on the cloud wind problem, and I am just going to highlight a few studies from the past couple of years that have actually approached this in the parameter space that's relevant for galactic winds. And so on top here, I'm showing work by Scannapieco and Bruggen, where they actually looked into if you had clouds of order 100 parsecs in radius that were 10 to the 4 Kelvin or so, the sorts of things that we might see in these winds, in a background that is created by the supernova explosions. How long does it take that gas to get mixed in, and how much does it accelerate? These were calculations that were done with radiative cooling and an adaptive mesh refinement code. The max resolution that they were able to achieve is about 64 cells across the cloud radius. You really need high resolution for this problem, or you won't correctly characterize the instabilities that actually result in the breakup. Also last year, there was a letter published by Mike McCourt and collaborators that was looking into what happens in the case of a tangled magnetic field in this cloud that shows that the evolution is quite different between the MHD and the hydro case. So this was also looking at the question of how gas might be pushed in a galactic wind, but relatively low resolution simulations in this case. Another recent study that looked at the MHD case was this paper from 2016, but these simulations were very short. They didn't actually follow the evolution of the cloud for a long time. And the point is that all of these are very expensive simulations to run, and so despite all of the work that's been done on this topic, at this point, we were still in need of high-resolution simulations that include the relevant physics, but also realistic initial conditions. All of these studies start with spherical clouds of gas that don't really look like the gas that we see in the ISM or in the winds, and then you'd like to be able to capture the evolution of that stripped and multi-phase material over a relatively large volume for some substantial amount of time in order to characterize the actual gas in the winds, which none of these studies could do. So now I hope I've motivated you as to why we want to look into the issue of these multi-phase galactic winds from the simulation standpoints. So I'm going to pause, and I'm going to tell you a little bit about the tool that I've developed that allows us to do this. So the code that I've written is called Cholla, and it stands for Computational Hydrodynamics on Parallel Architectures. Yeah, right? It's pretty good. And so it's also a cactus that grows around Tucson, so that's quite nice as well. As I mentioned, it's a GPU-based code. At the moment, it is a static mesh code, and it incorporates state-of-the-art hydrodynamics algorithms, high-order spatial reconstruction, and a variety of other things that I'll get into in just a moment. And we do have radiative cooling and photoionization that we've incorporated using tables that we've generated using the Cloudy code. And so I also just wanted to highlight that this code is open source, and if you want to look at it, you can go to this GitHub link and check it out. And we've described all of the physics algorithms in a paper last year. So what motivated us to put a hydrodynamics code on graphics processing units? So if you've been paying attention, I'm sure you've heard of GPUs in that sense that they're this sort of the the fun new thing in computer architectures. And originally, GPUs were optimized for pixel rendering. That's why they're called graphics processing units. And the idea is that unlike CPUs that are really optimized for serial tasks, so they have a small number of very powerful cores, GPUs were optimized for parallel tasks. So you can imagine that rendering the color of different pixels on your monitor is something that can easily be done in parallel because one pixel doesn't care about another pixel's data. And so, instead of a few powerful cores, GPUs have, in modern devices, many thousands of not particularly powerful cores. So they can't be run as standalone devices. You have to plug them into CPUs. But if you have an appropriate problem that can be run in parallel, you can get very large speedups because you're able to do things simultaneously, even if you're doing each individual operation more slowly than you would on a CPU. And so I'm now going to run through sort of the basic idea of how Cholla works, not because I think it's important for everyone to be an expert in hydrodynamics finite volume techniques, but because I think it helps illustrate how graphics processors are useful in this context. And so what Cholla does is, we're solving the equations of hydrodynamics. We're doing it on a static grid, and we can do this in 1 or 2 or 3 dimensions. And so to walk you through the process of how that's actually done, you start with a grid on which you apply some initial conditions and some boundary conditions. And then you iterate through the entire grid to calculate a time step. So Cholla uses a constant time step for all of its cells. Then this is a finite volume code, meaning that each cell has a volume averaged set of variables, density and momentum and energy. And so in order to calculate how that fluid is going to evolve in the grid, what you need to do is calculate fluxes between cell interfaces. And so the first step in calculating those fluxes is to reconstruct the values of your conserved variables like density at the interface of a cell. And so you can imagine that you could do this a number of different ways. You could have a piecewise constant reconstruction where you just assume that the value at the edge of the cell is equal to the average. That's going to be a very diffusive method that's not useful for practical applications. You could also have a piecewise linear method. So this is slightly better. You use information from nearby cells to try to better reconstruct what you think the fluid actually looks like, or even a third order parabolic reconstruction. And which particular method you use might depend on the problem that you're trying to solve. But one of the things that's nice about Cholla is that we have a variety of different reconstruction methods. And so you can actually test whether or not the reconstruction that you're doing is affecting the solution to your problem. So then once you've actually estimated what you think the values of the conserved variables are at interfaces, you need to calculate the fluxes. And in finite volume codes, this is generally done using what's called a Riemann solver. And this is just sort of a schematic representation of how a Riemann solver works. But effectively, if you have a left state and a right state of your hydrodynamic variables, then you can find an exact solution for what the waveforms should be at any later time across that interface. And so here maybe you have a shock wave that's coming out, and then some sort of contact discontinuity and a rarefaction wave. It depends on what your initial state is. But the process of solving for this family of solutions is done with a Riemann solver, and Cholla includes a number of different types of Riemann solvers as well, which also allows you to pick the one that's best for your problem in that sense, or see if it's affecting your answer. And then the actual integrator that you use it can vary depending on in the corner transport upwind method, for example, you may want to use information from transverse fluxes to update in another dimension to get out of your one-dimensional problem and try to improve the accuracy or decrease the diffusiveness of your method. Again, the details of these integrators aren't particularly important, but having a variety is an advantage in that different problems actually work better for different solutions. Okay, so having gone through that, what do we get out of putting this calculation on GPUs? So basically, the idea is that a grid-based code, especially one on a static mesh, is a very parallelizable problem. So in order to calculate the fluxes across these interfaces and update your conserved variables, you really only need a small amount of local data. And so you could easily calculate the hydrodynamic variables for a cell on one side of your volume without caring about what's happening at the other side of your volume. You can do them in parallel. And in addition, the algorithms that have been developed to solve hydrodynamics, and in particular things like Riemann solvers, are very computationally expensive. So speeding those calculations up is often a way to automatically make your code faster. If you're doing something like gravity and hydrodynamics is always going to be what takes the most time. And so, of course, the idea is that with GPUs, we are going to parallelize that calculation and run things across these many cores, and that allows us to speed up the calculation by an order of magnitude or more as compared to how long it would take on a CPU-based architecture. In practice, the way this actually works, and this is sort of why I was going through how the hydro integration takes place, you have serial parts of the code, setting up the initial conditions, calculating the time step. Because every cell needs to know about the time step, it's useful to do those sorts of things on the CPU, because if you're doing this, say, on a cluster where you have multiple nodes, communications between nodes have to be done on the CPU anyway. The same is true for setting, for example, the boundary conditions. You may need information from a part of your domain that's not on that node, and so it's useful to be able to talk between CPUs. But then we transfer all of those hydrodynamic variables onto the GPUs and go through the entire hydrodynamics module without doing any more memory transfer. And because these integrators are quite complex and they involve a large number of calculations, we're able to do this step very, very quickly. And then we transfer things back at the end of a time step, and you loop around as many times as you need to for your problem. But because these steps are local, we don't need to do any communication, and they can be done entirely on the GPU. This is sort of more of a thematic representation of how things are done on the GPU. The idea is that if you're going to program for an NVIDIA GPU, you can write functions in this language called CUDA, and it's just an extension to the C language. So most of the code is written in C with a few additional functions. And those functions get launched on the GPU in units of these blocks. And so the nice thing about the GPU is that I just tell it that I want a certain number of blocks, and then I want a certain number of threads in those blocks. And essentially, each cell in my simulation gets assigned to one thread. So if I have 1 million cells in my simulation, I ask for 1 million threads. And then the GPU does the work of deciding when those blocks execute on the cores. So even though the GPU has thousands of cores, that's still fewer than the number of cells in my simulation. But I don't need to worry about scheduling each of those different threads. The GPU does that, and it does it very efficiently. That also means if they change the GPU architecture, so now it has a different number of cores or a different amount of memory, I don't have to change anything in my code. The GPU knows how to schedule those threads. And in addition, as I mentioned, you have to transfer memory back and forth between the CPU and the GPU, and that can be a bottleneck because the memory transfer is relatively slow. But we've designed the code to really minimize the number of memory transfers, and so we actually are able to do this quite efficiently. So we've rigorously tested Cholla, and I'm not going to talk about all of the different problems that we've looked into, but we're confident that it performs as well as or better than many other codes that are out there. And I'm just going to highlight a few of the tests that we've done just to sort of emphasize this. In particular, one of the things that's important in Cholla is that it has these unsplit hydrodynamics algorithms, and those naturally allow an extension to MHD where preserving symmetry is very important. And so just an example, here I've got a test. This is called the 2D implosion test. This is going to be a final state, and this is the initial conditions. And the idea is that you have a low pressure region reflecting boundaries and a high pressure region. And so when you let it go, it implodes towards the center, and then you have a bunch of shocks and rarefactions that bounce around in the box. But something that was pointed out in the literature is that if your code perfectly preserves symmetry, you end up with this jet that comes out from the corner, and if the symmetry is broken, you don't get this. And so it's a nice way to test whether or not you actually are preserving this feature in your code. And in our case, it's important because we hope to incorporate MHD in the near future. So this is a useful test case. Additionally, I often get asked about, well, it's a grid-based code and Cartesian coordinates, and so what do you do about the instabilities that arise when you have very nearly grid-aligned shocks? This is something called the carbuncle instability, and this is just the end state of a test that often displays this instability. And the idea here was that you started with very, very low pressure gas that is, velocity. The velocity lines are going in towards the center, and then when you let it go, it drives a shock outwards. So this is density. High density is red, and low density is blue here, and density contours overplotted. And as this very strong shock is propagating outward, you end up with these instabilities along the edge that if uncorrected, can completely ruin your solution. In Cholla, we've corrected this using a method that basically incorporates information in that Riemann solver, which is fundamentally 1D. It incorporates information about wave speeds from transverse directions, and that corrects for this instability. So the main feature of Cholla that makes it special is that it allows you to do extremely high resolution calculations. And so here I'm just showing a 2D Kelvin-Helmholtz test. Kelvin-Helmholtz, for those of you that have not seen it before, you start with fluid of one density, fluid of a different density moving in the opposite direction. The velocity shear results in these instabilities. And in this case, because we started with a discontinuity, the instabilities are seated at the grid scale, and then they grow. So you get small eddies that turn into larger and larger eddies. So in this particular case, the point is just that this was a calculation that's basically like double HD resolution that we did on a single GPU. So this is the kind of GPU that I have in my laptop. You can do these really massive calculations, and so when you put them together in something like a cluster, it really gives you a lot of power. So we don't have to watch that, but it's kind of nice. This is my screensaver, by the way. So. Okay, so one of the most important questions if you're designing a code to run on cluster scales is how does it scale? And so weak scaling is the idea that if you have one processor and you give it a certain amount of work, then if you have 10 processors and you give them 10 times the amount of work, it should take the same amount of time as it took you to do 1/10 the work on one processor. That's called weak scaling. And for me, this is the most important kind of scaling because the idea is that I would like to do really massive calculations across thousands of GPUs. And so I want to make sure that as I'm increasing the problem size, I continue to get the kind of performance that I'm looking for. And so we've actually, in doing these scaling tests, we've run Cholla on up to 16,384 GPUs. This is on Titan, which is the largest supercomputer in the US that we know of. And what we see here actually is that the integration step, so this is all of the hydra which is taking place on the GPUs, the scaling is completely flat all the way out. We lose a little bit of time on the communication step. Here, the rapid jump at first is just because if you only have one process, then you're not doing any communication, and so it's hard to beat 0 time. But once we get up to 8 processes, the communication time is also flat, and so the code really it's excellent weak scaling on up to the largest machines that we can run it on. Right. So this largest simulation that we ran was 500 billion cells, so really a very large volume hydrodynamic simulation. In addition, I've recently included radiative cooling in the code, and I don't have time to get into the details of this, but if you're interested at all in hardware architecture, this was a really cool thing that we discovered. Basically, the GPU has built-in interpolation functions, and this is, again, harkening back to its days as a tool for video game processing, but we were able to use those built-in interpolation functions in order to do interpolation on our our radiative cooling tables. And that means that, here I'm showing lines, dashed line in this case is actually the radiative calculation, and the solid line is the adiabatic calculation. Again, this is a weak scaling test, but the point is that it actually takes the exact same amount of time now for us to do a radiative calculation as adiabatic. So, one of the things that you gain on the GPU is that adding more physics is good, because really you just want to load as much computation on there as you possibly can for the amount of memory that you use. And so this is another cool feature of the code. Okay, so now that I've given you sort of a brief overview of how Cholla works, I'm going to talk a little bit about what I've been doing with it. I've always been interested in galaxy evolution, and this galactic wind problem I thought was an interesting one because, as I said, it's going to benefit from really large volume simulations with high resolution, and that's something that Cholla is very good at. So, sort of getting back to the wind model that I was talking about at the beginning of this talk, the idea is that if we have a starburst galaxy, and here again I'm showing M82 so you can see the disk and then the wind that's flowing out, there's this starburst in the center, and that's going to create this bubble of very hot, overpressurized gas, which is then going to expand and cool adiabatically, primarily. And if we assume that that expansion is roughly spherical, which seems to fit the data okay in the inner regions, then you can analytically calculate what the density and velocity and temperature of the hot gas will be at any given radius from the starburst. And so that's a wind model that was developed by Chevalier and Clegg in 1985. And so then, as I mentioned, we see these cooler clouds of gas. In this case, cool means 10 to the 3 or 10 to the 4 Kelvin, that are, appear to be embedded in the hot background that you don't see in this image. But given that we see them there, that means they must be exposed to this hot background wind. And so the idea in our simulations is that we want to zoom in on this particular process. So if we put a little box on this region, blow it up, then this is what one of our simulation volumes actually looks like. So we have, these clouds, and in this case, we're studying clouds of gas that have density distributions that are set by turbulent processes, so log normal density distributions. And then, in the background, you'll have this hot wind, and the question is how is this cloud going to evolve over the course of its lifetime? So now I'm going to show you a series of movies, actually. This is what one of these simulations looks like. And here I started with a cloud that had a median density of 0.5 per cc. There's some other parameters here. This is the whole box, actually, that's being shown up here. And then this is, if we zoomed in. Thanks. And these movies are density projections. So the intensity is set according to the density, and then the color corresponds to the temperature of the gas. So cooler gas is purple to blue, and then the sort of 10 to the 4, 10 to the 5 Kelvin gas is in green, and then the hot gas is actually a reddish color that doesn't really show up on this background. So this is, the general idea is that we follow the evolution of this material as it's interacting. And one of the things that we could do with this study that hadn't actually been done before is look at what the multi-phase structure of that wind interaction is. And so this is, again, just a movie of that same simulation, actually, where I'm showing a phase diagram. So you've got density on the x-axis and temperature on the y. We start the cloud in pressure equilibrium with the hot wind. So here, I'm just showing all of the cells that are actually in the box, colored according to sort of where most of the mass is. So you can see that there's always a lot of mass in the wind, but at earlier times, there was more in this cloud. And we can watch it evolve in phase space. So I'll actually start this movie again. Right, you can see the cloud was distributed initially in pressure because it was a variety of densities. You can see this this dashed line represents where heating balances cooling in these simulations. And so initially the cloud cools a bit, but then once all of it's been shocked, it moves over into this parameter space, and some of it is able to cool quite effectively, and then it just sits down here on this locus. And in general, it evolves roughly in pressure equilibrium with the hot wind. So then, basically, gradually, material moves from these higher density cool regions in phase space sort of up along until it gets incorporated into the hot wind.
So what's the total linear distances traveled by that?
Right. So, in terms of the high density material or the intermediate stuff? Right, so effectively gas that's over here doesn't move very far at all. And these simulations, of course, it depends on how big your initial cloud is. Ours is 5 parsecs, and the really high density gas moves like, a few cloud radii.
So that moves at some modest multiple of its internal sound speed?
Yeah. Mm-hmm. So actually here, I'll show, this might be interesting. So this is going to be a density velocity diagram, same thing. So here, the cloud material starts out 0, and you can see that, right, basically the velocity depends very highly on the density of the gas. You don't do a very good job accelerating this high density material. So there's some material that's sort of intermediate densities that reaches a few hundred kilometers per second. But one of the things that was interesting about this plot is that in these outflows, you actually observe, material in H alpha that's moving at 600 or 800 kilometers a second, and that's not going to be explained by an interaction like this. We're not able to accelerate that gas to the velocities that's seen, indicating that perhaps ram pressure from the hot wind isn't enough to do it.
But it also looks like the cold material is eventually dissipating over some relatively modest linear scale compared with, 10, 12 parsec.
Right. Exactly. Yeah. So in these simulations, right, that's the other piece of it, is some of the cold material, we didn't actually turn on gravity, but some of the cold material could fall back in sort of a fountain effect, like the densest regions. But much of the cloud is just getting, incorporated into the hot phase. And so that mass loading actually, as I'll get to in a little bit, is going to be important for our conclusions as well. Yeah.
Radiation pressure and line driving and things like that at all?
No, so we've not included radiation pressure. This is just solely a hydrodynamic calculation. So we've also looked at, how does the momentum couple to these different phases? This is something that I was alluding to in talking about the velocities. The idea is, we start with, this is a histogram of the density and then, momentum in units that don't matter for these purposes. But initially you start out with a log normal density distribution, and as the cloud is compressed, that gets moved over, but you're approximately sharing momentum the way you would expect, roughly evenly across the phases given the mass. But then cooling leads to you having this peak in density in these sort of intermediate density regions, and then as the simulation goes on, you end up much more effectively transferring momentum to those phases. And so again, the highest density gas in our simulations really doesn't move very much. If anything, as it starts to move, it just gets rarefied and incorporated in these lower density phases. So something that was unique about our study, as compared to what people had done previously, as I mentioned, is that everyone else had been doing this with spherical clouds. And so we thought, well, the clouds that are observed in these winds aren't spherical, so perhaps the density structure is an important component. And so here I'm showing 2 clouds that have the same median density. This is the simulation that you've actually seen before. What you can see is that the original density structure has a huge effect on the subsequent evolution of the cloud. So in the case of the sphere, it basically compresses from all sides into a very high density core, which will then eventually get broken up. But that high density small area means that it actually is able to resist mass loss for a much more significant amount of time than the turbulent cloud. The turbulent cloud is sort of immediately broken up into all of the sort of high density pockets, each of which then evolves effectively as its own little cloud. And so this process, of course, is also resolution dependent. But the point is that in the case of the spherical clouds, you're able to also more effectively accelerate the material because you're pushing on it all sort of evenly initially.
There's some similarities when you talk about the spherical one as just being like the log normal one, but with an extra push.
Perfect. Yeah, yeah. Well, in effect, that's sort of what it gets to is, right, as you, if you, with the log normal one, if you basically decrease the Mach number, then eventually you just get to the spherical case. And so it's similar. But for the same median density, you more effectively accelerate the gas in the sphere. And so here I'm just showing how the mass loss proceeds for those simulations. Again, the time is just scaled according to this characteristic time scale, the cloud crushing time. And this is the mass in the cloud as a function of the initial mass, where we're just calculating cloud masses, everything above a certain density threshold. And what you can see is, the turbulent cloud loses mass much more rapidly than the sphere. And this was actually in contrast to adiabatic calculations that we did, where we found that if you calculated the cloud crushing time using the median density of the turbulent cloud, then it actually tracked exactly with the sphere according to this characteristic time scale. And so, sort of in more detail, if I show this is the highest resolution simulation we did, had 1.2 billion cells, so just double the resolution of the previous simulations. What you'll see when I start it is that in the case of this turbulent cloud, the shock is propagating at different speeds through different density regions. So you can actually see that happening here. And as a result, you much more quickly are able to incorporate the lower column density regions into the hot wind. And so then you have all of this mixing that's happening in the region behind the cloud. And then you have all of these little high density pockets that form their own little clouds that have their own little bow shocks, although that doesn't show up in this projection. And so, a question that we have that at the moment we haven't resolved is, what would happen if you kept increasing the resolution in this problem? Theoretically, at some point, some other physics is going to take over, but I think the point that we were making is that this situation is going to be really very different than what people have been calculating when they're using these 100 parsec spherical clouds. That's just not very representative of the physics that's actually taking place in the winds. And so, again, when we have a turbulent distribution, this is back to the phase diagrams, that phase structure that you calculate is also very sensitive to the initial conditions of the problem. And so with the sphere, you get a large amount of mass in these high density, in the high density gas and very little multi-phase material, whereas in the turbulent cloud, you always have a lot of multi-phase material. So if you were looking at observations of one particular phase, say you're looking at the H alpha and you're trying to calculate how much mass is in the wind as a whole, then you're going to get very different answers if you assume something like this picture versus the actual multi-phase wind structure. And as I already alluded to, the same is true for the velocity of the material. We were actually hoping, well, not hoping. It would have been interesting if higher density material were easier to accelerate in the case of the turbulent cloud, because as I mentioned, that's something that is currently unsolved, is how you actually get intermediate density cool gas moving at high speeds in these winds. And in fact, with the turbulent cloud, the problem is much worse because the intermediate density regions just get incorporated quickly into the hot wind, and the highest density gas moves less quickly than it does in the spherical case. So this is not a solution to that problem. In fact, it makes it a bit more interesting. So we've also, we looked at how the surface density of the clouds affects their evolution. And here I'm just showing, sort of the fiducial case was n equals 1, going all the way down to n equals 0.1. And what you'll see as I start these simulations is that the density is very important in that when the gas gets shocked, some of it in the turbulent cloud is able to reach densities that allow it to cool very rapidly, and that's going to extend its lifetime a lot. And some of it just heats enough that it's never able to cool, and then that gas gets very quickly incorporated into the hot wind. And so you can actually see the reddish orange stuff, especially in this lowest density case. Most of the cloud is immediately incorporated into the hot wind. If we had lowered this density a bit further, then you probably wouldn't have even ended up with any of these cold clumps. And these two actually are evolving very similarly. But again, this is because we have enough gas that's over the threshold density that it can cool and compress, and that increases the lifetime of these clumps a lot. Something else that's relevant about these calculations is we allowed the gas to cool to lower temperatures than other people had. And so, if you set a cooling floor at 10 to the 4 Kelvin, then you're never going to see gas exhibiting this behavior in the simulations. So that was something else that was sort of interesting.
10 to the 4 Kelvin is sort of a characteristic cooling floor for cosmological or galaxy conditions.
Right. Yeah. But I think in winds it's less obvious that gas should only be cooled to 10 to the 4 Kelvin, especially since you see lots of molecular gas in the winds. And so this is just showing how that mass loss proceeds as a function of surface density. And because I've scaled out the density, the cloud crushing time, as you may remember, incorporates the actual cloud density. And so you can see that the two higher density solutions track pretty well. And then as you get to lower densities, more of your gas is following an adiabatic line. This is what happens in the adiabatic case. And that line just will continue to move over. And the same thing is true for the spheres, but the transition is much more dramatic since all of the gases are the same density. You basically go abruptly from the evolutionary track that you get in the case where it's able to cool effectively to the evolutionary track that you get when none of the gas is cooling. So how does this connect to sort of the bigger picture of galactic winds and current observations and in cosmological simulations? So an idea that's been suggested recently by Todd Thompson and others is that one of the ways that you could get cool gas in galactic winds moving at high speeds is if you actually managed to cool gas out of the hot phase. So as I mentioned, you've got this hot gas that we think is traveling at 1,000 or more kilometers per second. And what these plots show is, as a function of radius from the galaxy and temperature here, and radius from the galaxy and velocity here, the amount that you mass load that hot gas, here beta, which is going from 0.2 to 1.6, beta is basically how much more mass have you incorporated into the hot phase as compared to what you would expect just from the supernovae. And so as you increase the mass loading, you actually are able to undergo thermal instability at relatively small radii in this hot phase as it's cooling adiabatically. And then this gets you down to gas that's of order 10 to the 4 Kelvin. And it's going to be moving at hundreds of kilometers a second. And so, this picture depends heavily on how much you can mass load the gas. But in fact, this is sort of a schematic of the process. The idea is that if those entrained clouds, like the ones that I've been showing you in my simulations, are destroyed quickly, and the gas is incorporated into the hot phase, then that's what allows you to cool at these radii from roughly 1 to 10 kiloparsecs. And my simulations actually support that picture in the sense that we weren't able to accelerate gas very effectively with these turbulent structures, but we were able to much more quickly mass load the hot phase as a result of having all of these different column densities. And so, this is a picture that I would like to test in the future. And so I have a plan for doing that involves some really large-scale simulations. The simulations I've been showing you so far are large in the sense that they're quite high resolution as these things go, but they took maybe of order 1 million hours on Titan, whereas your typical InSight proposal is something like 100 million hours. So I put in an InSight proposal to do simulations that look more like this, where the idea is we would have really a very large box. Here, it goes up to 10 kiloparsecs above the disk, a gas disk with M82-like parameters in terms of the size and the region where you would include this supernova feedback. And the idea is that this simulation box is large enough that it allows you to have the spherical geometry you need in order for that hot wind to cool. But we can do this with resolution that's of order, a few parsecs, which is high enough resolution that we should actually be able to capture those thermal instabilities if they're going to happen. And so we can change parameters like the mass loading depending on how we do the supernova feedback, but we should actually be able to test this picture of whether or not you actually do get winds cooling out.
So this picture depends on adiabatic cooling. The n squared cooling
Yes.
clearly goes like, well, a fairly strong negative power radius, right?
Right.
So if you don't cool right from the get-go, you're not going to cool further out unless the temperature is
Right.
and you make use of the cooling function.
Yes. Yeah. So it absolutely does depend on adiabatic cooling. I mean, that's the idea is that you know, the adiabatic cooling, if you cool if you radiatively cool fast enough relative to the adiabatic expansion, which you only get in this narrow region of parameter space where beta is, you know, of order the values that I was showing you, then the radiative cooling actually wins out. But if you're not in that region of parameter space, then even though you're adiabatically cooling, you never are dense enough at the right temperature to undergo thermal instability.
There's a minimum mass loss rate that for which this will work. I mean, below critical hot wind mass loss
Yeah.
rate, you're just not going to have enough n squared, right?
Yes, although,
You can trade off a little bit,
right. And there are other parameters
but
that matter, like, you know, what's the thermalization efficiency of the gas, you know, in the ISM, and that depends on where you put the supernovae. And so yeah, there are a few factors that go into it.
The point was that my say this occurred that after you drain the whole gas that you
Yeah.
pulled diagram, right?
Oh, yeah.
Pulled it out.
Right.
Then the combined mass outflow has to be above a certain level. It won't work.
Right, relative to the star formation rate. Yeah, no, that's true. So there's, you know, effectively a threshold density where this would, I mean, yeah, a threshold
that
star
makes
formation
sense.
case. Yeah,
Astrophysics.
right, exactly. Yeah, so actually that's basically what I had. So I can quickly summarize, but the idea is that, you know, as I've showed you, these are really complicated structures, and, you know, they're going to be important because the rate at which gas is flowing out of galaxies affects their subsequent evolution, things like their star formation rate, and we need to understand them in order to interpret observations. And we can use our new code, Cholla, in order to start to tackle these problems. And, you know, the particular simulations that I've been talking about today demonstrate that the initial conditions of these problems are very important, and that you get this momentum coupling to many phases, but your high density material is not moving very quickly. And so this mass loading, as we've just alluded to, may have important implications for the way that the winds evolve. So that's all I have. Yep. Any further questions? Yes.
So, a couple pieces of physics that are not in the code came up. I just wanted to name them and ask your opinions of how they affect the result.
Okay.
So, one was radiation pressure.
Yeah.
Another one was line driving. Another one was you showed a slide with NHT in which the evolution was very different.
Right.
And then the third one that wasn't mentioned was electron thermal conduction.
Yeah.
So, add these three things in, how do you think the results would change?
Right, and so I think the answer is going to depend on the exact systems that you're interested in. So radiation pressure is an interesting one because I think, you know, it's going to be most important in systems where you've got a lot of dust. And I think for the purpose of these simulations, I think radiation pressure is going to be not as important because I'm assuming that there's not a lot of dust actually in these outflows, which may or may not be fair. But I think, you know, in terms of what's actually happening in the disk of the galaxy, I think that's where radiation pressure is going to be crucial. So, you know, I'll sort of punt on radiation pressure for the moment, but just say that, you know, in these outflows, we're just assuming that there's not a lot of dust and that radiation pressure is not going to be the dominant term over the ram pressure. So thermal conduction is, yeah. So that's also one where we've thought a little bit about it, and you know, in terms of the exact parameters in our simulations, we think it shouldn't be an issue, in the sense that actually. Evan Scanapieko and Marcus Bruggen wrote a second paper after the one with the simulations I showed, where they did look at the effects of thermal conduction, and basically if the clouds were large enough or had large enough column densities, then thermal conduction didn't affect the evolution a whole lot. In that, it could have smoothed out the instabilities that would change the way that things were breaking up, but in fact, they found sort of similar effects to what we found due to the cooling, which was that it resulted in the clouds compressing more, which just then makes it harder to push on them, and so it sort of delays the lifetime of all of this evolution happening, but doesn't actually change the end results. So I think that's something that we would like to look into, but I don't think it's going to have a huge effect. And then the magnetic fields is the really interesting one, because people have claimed that it's gone all different ways. So up until the McCourt paper, actually a lot of papers were claiming that, well, depending on which way your magnetic field is oriented, it actually can increase the instabilities, and things happen faster. Then the McCourt paper came out and said, well, if you have this tangled field, then it helps hold your cloud together. But those are relatively low resolution simulations with spherical clouds. And my simulations show that as you increase the resolution and as you add these more realistic density structures, you go the opposite direction. And so something I really like to do is see, well, what if you have a turbulent high resolution cloud with a tangled field? Does that change the results? And I really have no idea which way it would go. So one of the things I'd like to do is add MHD to the code, and then that's probably one of the first things I'll test, just because it would be relatively simple.
Do you think this code could be useful for cosmological size simulations over 100?
It depends on what you want to do with it. So right now we don't have a gravity solver, although that's in the works. If you wanted to do something like, a calculation of Lyman alpha forest, it would be really useful. If you want to calculate what's happening in galaxies, it's not going to be, because we'll never have high resolution on the galaxies themselves, and so you always are going to want to go with an SPH or an AMR, hybrid code for those. But I think it's interesting to think about the kinds of problems that can benefit from very high resolution with static grids, and there are some cosmological problems that would.
Curves. I mean, you're starting off with the gas, hot gas moving fast.
Right.
Cold gas. But supposed to accelerate better. There's enough cross section in the cold clouds that there's enough pressure in the hot stuff to just accelerate as a sort of a single medium.
Yeah. So that's one of the reasons I want to do these sort of big global disk simulations, is because I actually think that the geometry in the initial conditions is going to change the results a lot. And so, I think that there's certainly merit in the simulations that we've done, especially because we've shown, what sorts of scalings you shouldn't take away from, idealized spherical cloud simulations. But I don't think that the final answer is going to come from a box like that. And that's one of the reasons, right, is that you're not really representing the situation that's happening. Certainly, I think ours were fine because we said this is what it looks like at 1 kpc. We see these clouds. Let's see what should happen to them in that scenario. But right, I think in terms of the acceleration, I really think we have to get the right geometry and actually start from the disk gas to see how that's going to work.